Good morning. And as always,
slow is smooth and smooth is fast.
So what we have is a problem where we're both running in a race. And I'm going to run 1 mile in 6 minutes, and Mr. Roberts is going to run 2 miles in 12 minutes, or 12 minutes to run 2 miles. Who wins? Who's faster?
And the answer is we have the exact same speed. We're just as fast. We both actually can run 1 mile in 6 minutes.
So that's the question of the difference between speed and velocity. So this idea, how fast you're moving over how much time is going past.
So speed and velocity are rates. And anytime you hear the word rate, think fraction. And most of the time in physics, when we talk about rate, we do mean something changing with respect to a change in time. So here we see delta x, displacement, over delta t, a change in time.
And there are two different ways that we can look at speed and velocity, average and instantaneous. A good example is if you're driving down the street and you have that jerk driving next to you that speeds up to 100 miles per hour and then brakes when they get to the person in front of them down to 20 miles an hour, but you sit at a standard 40 miles an hour and you get to the next stoplight, you'll get there at the exact same time. So your averages are the same, but your instantaneous acceleration speeds and velocities are all different.
So we're going to kind of build our term variable unit document. When we talk about average speed, we're talking about distance over elapsed time, or the time that occurs.
So once again, since there's no variable for distance, there can't be a variable for speed. So we have no variable, but we still do have a unit. Meters per second is the average speed.
And then we have velocity. And average velocity is displacement over change in time.
And our term is average velocity. So B equals, and then we have a AV as a
in the subtext here.
Subtext.
And really just remember that has no mathematical bearing, that doesn't do anything to the variable or to the number. It's our way of just kind of identifying that this is something or something else.
And then it's meters per second, meters over second. You'll notice the units for both are the same. It's how we treat it that's different.
And something to kind of consider, speed is always positive, while velocity can be either positive or negative. And we'll go into this idea of scalar and vector. And the way I remember this is when I'm driving in my car, my speedometer, my speedometer, always goes from 0 to something, no matter what direction I'm going. It's a speedometer.
And our example that we have in this problem is that we have a student that runs a position marked 0.0 to a position that was 100.0 meters in 14.5 seconds. What is the student's velocity?
So take a moment, knowns unknowns equations.
All right, so let's take a look. So we've taken our 3 numbers and matched them up with the 3 respective variables. We've identified the 2 unknowns that we've asked for, and we've written out the 2 equations that match with those.
And you'll notice the problem never says what is the student's displacement, but unfortunately we need to know what the displacement is to solve for velocity. So even though velocity is all that we're asked to solve for, we recognize that displacement is an unknown that we do need to solve for.
So take a moment, solve it. So the first thing that we need to do is we need to solve for delta x, or displacement.
We do that by taking the equation, substituting our variables, solving.
So our displacement is 100 meters, and then we need to solve for our velocity now that we have our displacement.
Yeah. And you can see as you follow along that we did make a small error on our notation, really my notation, that I dropped the point zeros for my 2 position measurements, and that actually influences my significant figure problem. So that's something that I'm going to have to correct in my own work, and we want to really encourage you to maintain your significant figures.
And then, so going back to the velocity, and then we substitute our variables, and we solve. So this goes back to its point. If we have 100 divided by 14.5, we can't just leave this big long number because it's not accurate to what we actually measured. So we need to use our significant figures to round the answer appropriately. And so our answer was rounded to 2 significant figures.
What's important, we really want to emphasize, is your calculator is going to give you that long number. You don't want to rewrite that really long number. And in fact, you want to avoid using that really long number in your calculations.
So the answer is the student's velocity is 6.9 meters per second.